Hello there. In this video we're going to talk about techniques that are used to solve integrals involving trigonometric functions raised to some arbitrary power. So the integral that we're not going to be focusing on are integrals that can be easily used via substitution. For example, the integral of sine to the 51 to the power of x times cosine of x dx, where you can simply let u be sine, so the substitution derivative cancels with the cosine, and then you just have a power rule to deal with. So we're not going to be dealing with that. What we're pretty much going to be focusing on are integrals of the form, the integral of sine to some power k of x dx. So once you know how to deal with this integral, you can use it as an exercise to pretty much establish similar results for integrals of the form cosine k of x dx. For example, cosine squared, cosine cubed, cosine to the 50th power if you want to. And if you're feeling really ambitious, you can extend this to something a little bit more general. For example, the product of sine to the k of x times cosine to the L of x dx, where k and L are some natural numbers. But this is the integral in this video that we'll be focusing on. Alright, so I'm going to assume that we at least know the basic integral of sine and cosine, namely the integral of sine of x dx is minus cosine of x, and the integral of cosine x dx is sine of x. So those are some basic prerequisites. Also for this video, you need to know some basic trigonometric identities that can be really useful, namely sine squared of x plus cosine squared of x is equal to 1, the Pythagorean identity. And we'll also be taking advantage of the half angle identity as well. So remember that sine of x divided by 2 is going to be equal to plus or minus the square root of 1 minus cosine of x divided by 2. So if this is true, we can square both sides of this expression to get sine squared of x over 2 is equal to 1 minus cosine of x over 2. We can replace x with 2x, canceling out this 2, and that's going to give us the expression sine squared of x is equal to 1 minus cosine of 2x divided by 2. So we'll be using that a lot. We'll be using that a lot, and also verify in a similar way that cosine squared of x is equal to 1 plus cosine of 2x divided by 2. So we'll be using these three trigonometric identities very often. So with that being said, let us start with our discussion of our integral of interest. So example 1, the integral of sine squared theta d theta. So we're going to begin by using this identity here from the start. So we're going to rewrite sine squared theta with the 1 minus cosine 2 theta over 2. So it's going to be equal to the integral of 1 minus cosine of 2 theta all over 2 d theta. We can decompose this integral into two integrals. So we can rewrite this as the integral of 1/2 minus 1/2 cosine of 2 theta d theta. And then we can distribute this integral over these two terms and integrate. So the integral of 1/2 is going to be 1/2 theta. The integral of cosine is going to be sine, and then we need to use a backwards chain rule or a basic substitution to figure that out. So it's going to be equal to 1/4 sine of 2 theta plus some arbitrary constant c. So that gives us the integral of sine squared. So if we increase this just by 1, how much difficult does it get? So consider the integral of sine cubed theta d theta. So I'm going to begin by rewriting this as the integral of sine squared theta times sine of theta d theta. I'm going to rewrite sine squared using my Pythagorean identity. So remember that sine squared plus cosine squared is equal to 1, so I can solve this equation for sine squared to get 1 minus cosine squared. So this is going to be equal to the integral of 1 minus cosine squared of theta times the sine of theta d theta. And then from here, so I can let u be equal to cosine of theta because his derivative, or part of it, is sine theta, which is located there. So the derivative of cosine is going to be minus sine of theta d theta. So that means d theta is going to be equal to du all over negative sine of theta. So this is going to be equal to the integral of 1 minus u squared times sine of theta times d theta, which we found to be du over minus sine of theta. So we can cancel out our signs, and we can distribute this negative inwards to make it u squared minus 1. So we have this is equal to the integral of u squared minus 1 du. So we can just use a power rule on here, and remember u was set to be equal to cosine of theta. So this is going to be equal to 1/3 u cubed minus u plus some arbitrary constant c. And then we need to replace our u back into terms of theta to get our answer. So it's going to be equal to 1/3 cosine cubed theta minus cosine of theta plus c. Alright, so let's increase the difficulty just a tad bit. Let's consider the next exponent in sequence. So example 3. What about the integral of sine to the 4th theta d theta? So we can start this problem just like we did in the last one by decomposing sine to the 4th as sine squared times sine squared. So this is sine squared theta times sine squared theta d theta. So we can rewrite sine squared theta using our double angle identity. Or you can rewrite this using the other one if you want to. I'm just going to use the double angle identities directly. So sine squared theta is the same as 1 minus cosine of 2 theta all over 2. Sine squared theta again is 1 minus cosine 2 theta all over 2. So then I can factor out a 1/4 to get 1/4 times the integral. 1/4 times the integral of 1 minus cosine 2 theta times 1 minus cosine 2 theta d theta. From here I'm going to distribute. So 1 times 1 is 1. I'm going to have minus 2 cosine 2 theta. That's an easy integral to deal with. And then I'm going to have plus cosine squared of 2 theta d theta. So this expression, so how am I going to deal with that? So we already know that cosine squared of x is equal to 1 plus cosine of 2x over 2. So what we can do is we can replace x with 2x to get cosine squared of 2x is equal to 1 plus cosine of 4x all over 2. So our integral becomes what? So 1/4 times the integral of 1 minus 2 cosine 2 theta plus 1 plus cosine of 4 theta all over 2 d theta. So I can decompose this fraction into 2. So I have a 1/2 and half of my cosine 4 theta. And I can combine my 1/2 and my 1. So 1 plus 1/2 is going to be 3/2. So 1/4 times the integral of 3/2 minus 2 cosine 2 theta. And then I have plus 1/2 cosine of 4 theta d theta. Now I can integrate over these three terms and get my simplified answer. So this is going to be equal to 3/2 theta minus, so the 2 and the 2 are going to cancel. That's going to leave me with cosine of 2 theta plus 1/8 sine of 4 theta. It should be sine. Plus some arbitrary constant c. I can factor out a 1/8 if you don't really like fractions inside of this. So if I factor out a 1/8, this is going to give me 1/32 times 12 theta minus 8 sine of 2 theta plus sine 4 theta plus c. But I think either one of these answers would be accepted by a reasonable professor. All right, so the next question would be what? So what about, so for example 4, the integral of sine to the 5th theta d theta. So odd powers of trigonometric functions like sine and cosine are very, very simple. You begin by taking out one of them, whichever them is. So we can rewrite this as sine 4 theta times sine of theta d theta. And what we can do is we can rewrite sine 4 theta as 1 minus sine squared theta, 1 minus cosine squared. So that's going to be 1 minus cosine squared theta, the quantity squared, times sine of theta d theta. And then we can let u be equal to cosine of theta. So du is minus sine of theta d theta. So d theta is du over minus sine. So this integral transforms into the integral of 1 minus u squared squared times sine theta du over minus sine theta. So sines cancel by design. I have a negative sign. I can't really do anything with that this time. So I'm just going to rewrite this as negative integral of 1 minus u squared squared du. Then I could use my binomial expansion tricks and rewrite this as 1 minus 2u squared plus u to the 4th du. And remember, u is equal to cosine of theta. And then use my power rule on this across each of the terms. So this is going to be equal to negative u plus 2/3 u cubed minus 1/5 u fifth plus c. So rewriting my integral in terms of what it should be, this should be minus cosine theta plus 2/3 cosine cubed theta minus 1/5 cosine fifth theta plus c. All right, so if you were to extend this, the next question would be what? So the integral of sine 6 theta d theta. Now some professors will just provide you with the generalized rule and then you just plug in the numbers and you get the answer. But I think that really lacks motivation, doesn't really show any purpose unless you're like, your goal isn't to learn the material, the goal is to just use it. But that's pretty much a subjective discussion to have another day. So what we can do with this, and I'm not going to finish this problem, I'm just going to show you how to start. So if you're interested, you can finish it if you want. So we can rewrite this as cosine squared of theta to the power 3 d theta. And we can, should be sine, so sine squared cubed. And then rewrite sine squared as 1 minus cosine cubed. So this is going to be 1 minus cosine 2 theta over 2 cubed. So I'm using my double angle identity here. So 1 over 2 cubed is going to be 1/8. So I have 1/8 times my integral of 1 minus cosine of 2 theta cubed d theta. And then you can use binomial expansion on this and use Pascal's triangle. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. So we're going to be on the third non-singular row. So this is going to be equal to 1/8 times the integral of 1 minus 3 cosine 2 theta plus 3 cosine squared 2 theta minus cosine cubed 2 theta d theta. So then what would you do from here? So you would expand that in whatever way you desire, and then we proceed in the same way as we did before. So in case you haven't already figured out the pattern, or some type of pattern, the answer will be in the form c times a theta plus b sine 2 theta plus c sine 4 theta plus d sine 6 theta plus c. And if you're feeling really adventurous and actually want to work this out, your simplified answer is going to be 1 divided by 192 times 60 theta minus 45 sine 2 theta plus 9 sine 4 theta plus sine, should be minus sine 6 theta plus c. And that is some strategies that you can use for trigonometric reduction integrals.